Okay, good morning, everybody. I hope you enjoyed the social dinner yesterday. Last day of this week's workshop. Format is the same. We'll start with 2 talks, short break, discussion with the speakers, lunch break, and then another panel discussion. And we are starting with our first speaker, Bianca Dittrich from PI, telling us about the area metric. The stage is yours.
How we get as a continuum limit area metric gravity and how that might be an interesting arena to explore. So spinforms are, a real-time path integral over quantum geometries. With real-time, I mean we can do both Euclidean signature, but if we do Euclidean signature, we use amplitudes with an I and Lorentzian signature. So that can be both easily formulated, just that it's not Euclidean quantum gravity, but Euclidean quantum gravity with an I. And it's very much related to Ricci calculus, again, not the original quantum Ricci calculus, which was done as Euclidean quantum gravity, but with an I amplitude. So it's path integral over piecewise flat geometries. As we will see, an important difference is, however, that these Ricci geometries, which Renata already introduced, are replaced really by a notion of quantum geometries. And that will be important because that's where area matrix will come. So it's important that we have this real-time amplitudes, because Euclidean gravity version of Ricci calculus basically had a terminal disease. It's the so-called spikes, which are equivalent to the conformal factor problem. So what are spikes? These are basically vertices in your triangulation where all the edges attached to this vertex can become very, very long. So in fact, infinitely long. And there's an old paper by Jan and friends, which says in 2D already, this makes basically length expectation values ill-defined. So in 2D, the gravitational action is a topological invariant, but even if you go to higher dimensions, then these spikes capture the conformal factor problem. So even this spike configuration will be exponentially enhanced. And so that's one reason that these Ricci calculus and similar lattice approaches basically all failed, because if you did numerical simulations, you pretty much ended up in a phase where these spike configurations were dominating. Yeah, Jan said it doesn't exist. Anyway. No, as you know, it's a bit hard to come to any explicit data from Mr. Hamber, so like this. Well, I know it's straightforward to compute the action for this configuration, and you get an exponentially enhanced vector. And so I don't, yeah, I don't, anyway. So what one can do, however, in Lorentzian quantum Ricci calculus, so here I mean with an I, and anyway, we have done that in Lorentzian signature. In this case, you have the spike configuration with infinitely long edges. You have also a configuration with very long edges, which do not need an inner vertex. We call them spine configurations. So they only exist in Lorentzian signature. But anyway, you can compute the expectation values even of arbitrary power of lengths And these are finite for these spike and spine configurations. And here, just to say that oscillatory amplitudes are essentials, because the integrals in general do not converge absolutely, because here this result is even with arbitrary powers of the length. So you can make it really polynomial growing as much as you want. So this also applies to quite arbitrary measure, as long as it's polynomial, not exponentially growing. And so this shows that, well, with oscillatory amplitudes, you can basically avoid this conformal factor problem, or can hope to avoid this conformal factor problem. Okay, so, well, we did Euclidean quantum gravity non-perturbatively because that was much easier to compute. We had techniques like Monte Carlo simulations, and it's much harder to deal with oscillatory amplitudes. In particular, if you have sums and so on. I did work on developing techniques to deal with that, but I will not talk about this today. But we will see that basically the computational challenge is something, well, which is an issue for the field, of course. So going back to spin forms, as I mentioned, is a non-perturbative path integral over quantum geometries. So here I give you a few essential details to just motivate where these area matrix come from. They're based on the so-called Plebanski formulation of gravity, which comes from the 70s. So if you put in this expression here for the B field, star E wedge E, where E are the tetrads, you see that the first term gives you the Palatini action. But Plebanski was actually working with this two-form field, but then putting this as a constraint condition. The second term is a term which does not affect the classical equation of motion, so in some sense is quasi-topological. We put it in for a particular reason. Here, gamma is a so-called Barbero-Mirzi parameter you might have heard about. And it's it's a parity violating term. So it would have in the two epsilons. So this is the usual Palatini. This is a parity violating term. And that is a so-called Plebanski formulation. Now, why on earth would one use this rather complicated looking expression? So, and the reason is that the first term here, if you don't use these constraints, is so-called BF theory. In particular, B is an independent field, and then it's wedged with the curvature of a connection, omega. And so B acts as a Lagrange multiplier, so the equation of motion will be F equal to 0. And in fact, it's a topological quantum field theory. And so this topological quantum field theory can be exactly quantized as a topological invariant. You can also discretize it, but you don't lose the diffeomorphism invariance and so on. And so if you use this quantization, this B field, which has lots of indices, which are just not writing, this will be quantized via Lie algebra generators. The choice here depends on your signature, so SO3-1 or SO4. It's very similar to lattice-Young-Mills, at least in the SO4 case. And omega will be converted into Wilson lines or holomies of SO3-1 or SO4. And so if you use that quantization, B is a two-form, and here includes the tetrads, so there's some geometric information. In fact, areas are more or less the square of B, or it's an area square, which is a square of B. So it turns out that area operators, which basically then are just the Casimir of this group, have a discrete spectrum. And actually can show from the fact that they are discrete that areas are more fundamental than lengths, meaning that you cannot really reduce them to length variables, or to cannot put constraints so that they come from length variables, as we will also see more technically from trying to impose these constraints. So the first step of spin-form quantization is to use this quantization of the topological quantum field theory, which basically you can see is exact, is triangulation independent and does all kinds of wonderful things for you. And the second step would be to impose on the quantum theory these constraints. And so part of these constraints indeed is not problematic at all. They can be imposed sharply. But another part cannot be imposed sharply, because what happens in the quantum theory is that these constraints, this part becomes non-commutative. And we can understand that you turn these B's into Lie algebra generators, and together with this term, you get basically commutation relations, which involve now this Barbero-Amirsy parameter, which in some sense turns into an anomaly parameter. Now, because of this commutation relation, which eventually turns these constraints to be second class, you can only impose them weakly, which for the sake of this talk means you use Gaussians instead of delta functions. And so eventually what you have done is you have extended your quantum configuration space. And well, if you would have imposed this condition sharply, we would have just a tetrad formulation. But now we have fluctuations away from that. And well, we only recently realized that what you truly get is an area metric space. So it's something more general than length metric. Yeah. So this is the area squares. So in SO31, they can be also negative. The area square, and that's kind of via the Cayley-Menge. Yeah. And that you get something discrete is actually also in both cases is something more subtle, which depends on having this term. So otherwise you would get something continuous for space-like areas and something discrete for time-like areas. But because of this term, the space-like areas are proportional to gamma times natural numbers or something. Yeah. Yeah, only because you introduce a gamma, but then this also is proportional to gamma, whereas the time-like areas are always just n, it's just the natural numbers. So we have also an anisotropy, so actually similar to your case, that you have also an additional coupling parameter. So gamma plays these different roles. Okay. More questions? Okay. So that's, yeah. Yeah, 1 second. Okay, so area matrix are quite interesting and possibly convergence of several approaches. We do get it from quantizing the Plemanski formulation. And so one rough reason you can understand it is that the connection which leads to angles, these are based on well, if you integrate them to holonomies or Wilson lines, these me over one-dimensional things. And so they are conjugated to surfaces. So the canonical conjugation needs always to be the spatial dimension minus the smearing dimension of your object. So connections or angles in 4 dimensions are naturally conjugated to areas. And so that's the reason why you get areas. And you see that also that's why areas have a discrete spectrum, at least say in the Euclidean, because they are conjugated to compact angles. And holography, at least again in 4 dimensions, Well, more recently, I guess there are a number of papers which reconstruct geometry from entanglement measures, which are proportional to areas. So here you have areas appearing again. And some time ago, actually, Frederick Schuller was advertising area matrix very much as effective descriptions arising from string theory. Because the word sheet of a string gives you also an area. What is an area metric? So it's an object with 4 indices. These 4 indices have the same symmetries as the Riemann tensor. So there are kind of 2 forms in these two pairs are 2 forms, and then they are symmetric in these 2 pairs. We also require cyclicity as for the Riemann tensor. So overall, you get 20 independent components, and they measure areas, as you would guess, and then the dihedral angles between planes and tangent space. So they have 20 indices, 20 elements, independent elements, whereas the length metric has 10. So they are truly an extension of the length metric space. They're more general than length matrix. Each length metric induces an area metric via this simple formula. There are different proposals to reconstruct a length metric from an area metric. So I believe that we have a canonical way which goes via the Klemanski formulation, so via B fields, but it's difficult to compute. Schuller has another formula. Anyway, so that is not completely settled, but you can see that this is also an extension. Yeah. Yeah. So areas measures in the, well, if you're in continuum, it measures the areas of planes in tangent space. So you take 2 tangent vectors, and that's what you put in. That gives it. Yeah, yeah. Okay. So I explained that well, spin-form quantization leads to this extension of the quantum configuration space. Instead of length metric, we have truly an area metric space. But in this dynamical principle for Plebanski formulation, well, you had, it has this BF term, which is topological. And so to get the correct equation of motion for GR, it is essential to impose these constraints, it seems. But now we say, oh, we don't do it exactly for part of them. So in fact, then it's really the questions, do spin forms lead to GR? And in fact, well, that wasn't kind of possibly not so well discussed outside the community, but there were real concerns that spin forms do not lead to GR. In fact, I started these things partially to prove that they do not lead to GR. So in any case, and this really has something to do with this anomaly. So in particular, in the kind of in what was called a semi-classical limit, which is a bit confusing, it's a limit of having large areas. What you can show is that configurations are peaked on flat configurations, and curved configurations are suppressed. And you can really track that down, trace it back to the anomaly in the constraint algebra I was showing you, and the weak implementation of the simplicity constraint. Well, you can see that this was discussed for quite some time, and people were confused. There's also that, of course, a number of people said, no, that can't be. And but there was also the issue that indeed it was very hard to compute and test the equation of motion, even on small triangulations, which would really test the equation of motion. And so on these existing spin-form models up to 2020, but still for these models, this computation has not been performed, despite actually ongoing efforts to develop high-performance computation tools and so on. But in this case, it would be one triangulation, which includes at least one edge, because that would tell you an equation of motion for the edge. In our case, we had 6 simplices, so single, yeah. Well, if you go to spin forms, these single-digit things, I think they have on the order of 500 variables. So it's just that roughly. I would have to check how many variables they have in the full model, but it is indeed a bit challenging. Well, I think in lattice Young Mills you come much farther with that. Spin forms were always thought as kind of very fundamental final things. So for that reason, they were very complicated. I don't think that this is the case. I think you always need to use to apply a continuum limit and renormalization to them. So we built a model which captures the essential ingredients of spin forms. In that case, it's like the discrete area spectrum and the weak implementation of these constraints, but it was much simpler. And actually, you can construct it from higher gauge theory, which sounds more complicated, but interestingly leads to much simpler amplitudes. And so higher gauge theory, roughly the reason is because you have a 2 connection, which now is conjugated to something one-dimensional. And this one-dimensional thing is actually tetrads. And so in higher gauge theory, you have much more direct access to the length variables. Whereas in gauge theory, you really need to always reconstruct them from the 2 forms, which is complicated. Anyway, they are much more amenable to numerical investigations. So it's really seconds on laptop compared to weeks or months on HPCs. And that allowed us to compute the path integral for the small triangulation and test the equation of motion explicitly. So we have done that for a range of configurations. And here you see one example, which looks funny. So that is really the expectation value of a given area here divided by the classical solution. So it should be around 1 as a function of this Barbero-Emisi parameter. And the different colors correspond to different scales of the boundary values. And so what you see is, at least for this range, is pretty much equal to 1, so that is good. It does reproduce the classical equation of motion. Here you see oscillation starting, and then they got completely crazy. That's not too surprising because gamma is really this anomaly parameter. So you expect kind of that things work only for small gamma. And we tested different curvature regimes, so for different boundary values leading to different curvatures in the solutions. And for all these, it's even that gamma up to 0.1 is possible. And that was kind of a larger range than what was suggested by scaling arguments. Anyway, it is consistent with expectations from black hole entropy calculations. But this range also depends on the size. So basically, the smaller the size, you would also expect the larger range of gamma is allowed. So that was actually the first explicit test of the equation of motion in spin forms. You could still basically ask, well, that was really a small triangulation. So it's a discrete equation of motion. But you could ask, what about triangulations with many building blocks? Could it happen that all these additional degrees of freedom overwhelm or dominate in the continuum limit? And so, well, yeah.
Standing right X, moving linear 0.6 or 7, and it seems to, I think.
Yeah, I have to remember, I think, these are really based on sums. And you have some non-trivial effects if you sum over oscillatory amplitudes so that you can have resonance effects. And it might be something due to this. You get things like pseudo-subtle points, which look like it is a subtle point in the sum, but it's not at all a subtle point. So it might be related to this kind of. Okay, but I would not trust this regime anymore. That's my. So what about the continuum limit for effective spin forms? So, well, given that really doing explicit numerical calculations, well, we did it for the small triangulation, and we can push it a bit further, but it's kind of out of reach to do it for a very large configuration with many edges. So, but for this question, it's more about, well, is a chance that we get the correct equation of motion. So we will assume that we can do a perturbation series so that there is a state or a phase on top of which it makes sense to apply a background field expansion for the action which we are using. And so for effective spin forms, the action is given by what is known as area-Ricci action plus terms which kind of are combinations of constraints, so quadratic forms in the constraints. So the first question is, what is the continuum limit of the area-Ricci action on a regular infinite lattice? The area-Ricci action, so that was also mentioned, the Ricci action was mentioned in Renate's talk. So it's a discretization of the Einstein-Hilbert action. It usually depends on length, but we can actually replace the length by areas. So there are far more areas than lengths in a given triangulation typically. And that's the reason why it was also widely assumed that this action does not lead to general relativity, because actually the equation of motion seemed to suggest, again, that the solutions are flat. And that was a misinterpretation later, it turns out, but it's very similar to the first problem I explained, that you have far more variables and you vary with respect to these many variables, so you get stronger equation of motion. That's what you expect. But the perturbative continuum limit was never established. And just to say what kind of calculations we are doing, so a similar calculation has been done in the 80s by hand by Ruth Williams and Martin Rotschek, and so for length Ricci action. So they took really the discretization of, well, they took the Ricci action and put it on a regular lattice, a hypercubical lattice, where each hypercube was subdivided into simplices. And well, it's really a bit painful to calculate that by hand. I guess now on a computer, we can do that quite fast. But in any case, what one finds, now one really has these length variables and the triangulation of the hypercube. You will find that you have 15 degrees of freedom per lattice side. But you can kind of extract what are the massless degrees of freedom, including 4 which are gauge and actually the diffeomorphisms, the linearized diffeomorphisms. But the remaining 5 degrees of freedom are actually massive, and you need to decouple them to get in the end to linearize GR. And we can do that now also on all kinds of refinements of this hypercubic lattice. And what you find, you can get that to much more variables, like I forgot the numbers, so say but 30, 50, or 100. But you always find 10 massless degrees of freedom and many more massive degrees of freedom. And so you always find linearized GR in the end. And this can be also done for Lorentzian signature, as a small remark, is not totally straightforward, because first it seems to get infinities, but then they all cancel if you put them on this hypercubical lattice. And here, these masses, some can be also kind of negative. The subdivision of the the hypercube. No, you have your hypercubes, and rules use what I call the standard triangulation. I think maybe I have a picture at the end of the talk, and for instance, one triangulation I will use for area Ricci calculus, I put a vertex in each hypercube, and so you get more simplices per hypercube. In this standard case, you get 24, and I think I get maybe 50. I forgot the numbers. Yeah, and then you can subdivide further the cubes and the faces, and okay, let's do that for area Ricci action. So we can actually also linearize this action. This time we get, for the standard triangulation, we get 50 variables per vertex. And if I use a refinement which solves very technical, kind of some technical issues, I get 100, or if I use finite lattices, even more. But despite these many variables, again, I find only 10 massless degrees of freedom, essentially. So the graviton degrees of freedom plus 4 linearized diffeomorphisms, and all the rest has mass. And in fact, I can integrate out all the rest, and to lowest order in the lattice length, that means in this case second order in derivatives, it reproduces linearized Einstein-Hilbert action. But so we see that we have all these additional degrees of freedom, but they are all basically have mass on the scale of the lattice length. I mean, the background I have to choose. And so they're all very localized and don't play a big role in the continuum limit. One can also compute the next to leading order. And one finds, well, modulo discretization artifacts, a Weil squared term. And in fact, this correction can be explained by having an area matrix. So you can trace back exactly this order by constructing an area matrix for each hypercube. And as I mentioned, that there's more degrees of freedom than the length matrix, and integrating out these additional degrees of freedom leads to the Weil squared term. I will show that for the continuum. And why roughly? What we integrate out is the traceless parts of the area matrix. The trace parts give you the length matrix. And so they are kind of like the non-diagonal parts do give you basically the Riemann tensor, but you contract them only with the traceless parts. So that gives you Weil, and then it's basically just linearized calculation. You get Weil squared from contracting everything correctly. The Lorentzian signature works also. Again, there's an interesting effect that if we choose our parameters to be such that we get null triangles, so triangles which in the background are null, fluctuations around these seem to be infinitely suppressed. But that doesn't even affect getting the length matrix as an Einstein-Hilbert action. And here masses can be positive and negative. Again, I will explain that this happens in the continuum, and we were motivated to look at that because of this effect. Okay. So, well, I'm making these claims. It's not very it is insightful to look at the calculations, but I would show you 100 times 100 matrices, and that's not so appealing. So but I can show you the calculations if you're interested. Yeah. I can choose a parameter. So, in that case, I do the hypercube, not really hypercube, but it has a spatial length and a time-like length. And so if I choose these lengths to be 1 and -1, I get null triangles in the triangulation. If I choose them something different, I do not get null triangles. But I get, then the Hessian, however, has the Hessian, some Hessian entries go to infinity if I take this limit to 1 -1. And so that actually means that fluctuations, certain degrees of freedom, are infinitely suppressed. And I find that a very interesting effect, which should be considered more. In fact, we did such a non-perturbative calculation, and we asked in spin forms, can we peak around a null surface? And you would expect that that's not the case, because in spin forms, the area, that is basically the area eigenvalues come with what we call the spin, confusingly. But large spins correspond to the semi-classical limit, because in the action, you basically have J divided by H bar. So large spins correspond to semi-classical limit. So you would expect that small spin is very, very quantum. So zero spin should be very, very quantum. But even in this non-perturbative calculation, we found that we could actually peak on null hypersurfaces. So here you find basically that the Hessian has this infinite values, which means that fluctuations seem to be infinitely suppressed. So there might be something going on, that null surfaces, maybe they are more classical than we would all expect. But yeah, one possibly should make more sense out of it. But anyway, so it could be also something, well, because it depends on your discretization. So I'm not quite sure, but I think it's an interesting fact to be explored in the future. This is, well, originally these two papers are all Euclidean signature. This is Lorentzian signature, and these come. Sorry. So these two passed. these two papers, yeah, they have been all done in Euclidean signature, but well, like last week we did the Lorentzian signature, and we get the same results. Modulo that we cannot go to this, but the these that the limit, if we go to the parameters where the time-like length is minus the space-like length, we get some entries which are infinity, but even that does not affect to get the linearized gravity part. So these are only entries in the area metric. Anyway. Okay, so I mentioned that the effective spin form action is given by the area Ricci action plus these constraints. And so far, I've only spoken about the area Ricci action. So you can ask, what about these constraints? But in fact, these constraints only involve terms which are quadratic in these non-length degrees of freedom, which are all massive. And so you can look at your scaling of your Hessian if you organize. So the trick is always to organize all these degrees of freedom in a nice way so that they have homogeneous scaling. So they only change the mass terms. So they do not affect at all this linearized GR action. And only the global factor, basically a prefactor for the Weil square term. And so we see, well, if you believe that you can do this perturbative continuum limit, that resolves the flatness problem, but you really see that only in the continuum. So you see that something has a mass only if you are on a larger lattice, because you need a momentum dependence to set the momenta to 0. All the additional degrees of freedom are massive. We even do not need an explicit constraint implementation. As I said, basically everyone believes that area-Ricci gravity does not lead to GR, except that John Barrett insisted he did not quote that in his original paper, but he was very proud. But even if we do implement these constraints, the result does not change in an essential way. So that is a very nice result because, as you would expect, the continuum limit comes with some sort of universality. And, well, you know, different peoples define different models, also Daniela here. And they basically essentially differ only how the constraints are imposed, because the first part is pretty much unique in quantizing the TQ of T. But this does not seem to matter very much in the continuum limit. And one of the first, well, the first spin-form model was a Barrett-Crane model. And based on consideration on one simplex, people concluded could not lead to GR, but it actually does lead to GR. So it could still lead to GR. And Daniela is very happy about that, and he can explain you why. So this is actually, yeah, you know, so you could also do calculations with the Barrett-Crane. Again, that's not very popular, but the advantage again is that I think this is a magnitude simpler model than the models which are currently used, apart from the effective spin-form models. Okay. Well, now, if you don't like discretizations, okay, that's a part for you. So, interestingly, we can derive the same kind of action with a bit more even precision from the continuum. So now we are just in the continuum. And what do we have to do? So as I mentioned, spin forms come from this idea of a Plebanski action. And already some time ago, independent from these considerations, Kirill Krasnov introduced this idea of modified Plebanski action. So he replaced the constraints by potentials. Back then, he was hoping that there would be a renormalization flow which would only affect the potential, basically. And actually, well, Plebanski comes in a chiral version where roughly you have only half the fields. And in that case, even if you do this replacement of the constraints by a potential, you basically get GR. I will say deformed version. We will see this deformed version. But if you use a non-chiral version, which is actually the one used in spin forms, well, that leads to a B-matrix theory of gravity if you replace all the constraints by these potentials. So, and the potentials, you might understand, indeed correspond to a weak implementation of the constraints. So what we did is we mimicked the split of the simplicity constraints into these two sets. One is sharply implemented, the other is weakly implemented. So we replaced only the weakly imposed constraints by potential terms. And well, if you solve for the connection and this Plebanski formulation, you get actually an action in terms of the area metric. And well, that's kind of a complicated expression where the area metric appears somewhat implicitly, but you can calculate things in the linearization. If you do that and integrate out your non-length metric degrees of freedom, well, what you get is Einstein-Hilbert minus Weil squared, all in the linearization. The Weil squared comes with this non-local term, which you don't, well, which in this lattice approximation we did, you don't see. I mean, you can expand that. And to lowest order, you just get Weil squared. And so that's consistent with the continuum limit we got for the area-Ricci action. Okay, and the somewhat surprising thing, or possibly not, if you calculate the propagator for the spin 2 part here, you find that there are no additional poles. So actually, renormalization-wise, it wouldn't help very much. But on the other hand, we would not say that this is a UV completion of something. This captures just the effect of extending your configuration space to area matrix. Okay, and for that reason, I think Kirill Krasnov, I think, was the one who called it a deformation of GR, but it's also something with higher curvature derivatives, which does not lead to additional poles. So was a bit of a surprise. Okay, we will see. Well, I will see that here I integrate out the additional degrees of freedom, and you get this non-local formulation. If you keep the area matrix, that would be just second order in derivatives. So you can trade, as usual, higher derivatives for additional degrees of freedom. But here it's also something very geometric. It's the area matrix, which gives you these additional degrees of freedom. Yeah. Yeah. Is this 1 over m squared? You mean? Yeah. I know that's what comes out. um, uh, uh, well, it was interpreted that, I mean, you can actually, in the chiral formulation, you can interpret these are ultra-local terms, which you just integrate out and throw away. I mean, they make things even more divergent if yeah. Well, so far I don't do anything with it, but in this chiral version where you find the same result, well, I didn't plan to discuss that, but you can make a non-local field redefinition, and you can actually absorb these additional degrees of freedom into the matrix. And what you find then is what you find is just the Einstein-Hilbert term plus something which has no derivative at all. So just a mass term. Yeah, so this is due to an additional shift symmetry which you have. You can redefine. It's very similar to having a scalar field which you can redefine to psi equal to phi 1 plus phi 2 or something. So you can absorb it. Yeah. So maybe it's if you have a kinetic term which is only in phi 1 minus phi 2, so that's very similar to that. This H? No, sorry. This is I will show that in a second. This is after I integrated out all the additional degrees of freedom in the area metric to the length metric. I'm only on the linearized level where I can make this split uniquely. Anyway, so yeah, well, in particular, if you want to write the full action. But let me show, I will show this in terms of linearized area metric fluctuations in a second, and you see the structure of the theory. In any case, let me just emphasize again. So this effect, we would say, comes from the enlargement of the quantum configuration space from length to area matrix. But there are still lots of other effects, for instance, the discretization of the areas, which we do not capture by this metric, by this action. So we don't necessarily see that as a UV complete formulation of anything. So just capturing this effect of having areas instead of lengths. Okay, so if you hate spin forms and Plebanski formulation are too many fields, you could just say, well, let me just consider area matrix. And well, for area matrix, in principle, it would be nice to have like something like the Levi-Civita connection, but currently there's no agreement on that. But what you can do is to think about, well, again, to second order, for instance, what are all the possible actions I can possibly write down, which are invariant under linearized diffeomorphisms. And so indeed, you have these linearized area metric perturbations. You can split these area metric perturbations to linearized order uniquely in a length metric perturbation, H menu. And then you have these chi fields. So in principle, they're kind of self-dual, anti-self-dual, anti-symmetric forms, and so on. In the end, they encode 10 degrees of freedom overall. So and they happen to be spin 2 degrees of freedom. So 5 plus 5 spin 2 degrees of freedom. And so the most general Lagrangian you can write down, well, for the H metric, you have the Einstein-Hilbert Lagrangian, linearized. You have the kinetic term with, here I put a mass, so for the chi fields. And then H menu couples to the chi menu. So it's, if you consider them as matter fields, it's a very unusual coupling between matter and gravity. And so this coupling also just sees the spin 2 part of the graviton, or of the metric, so the graviton. And indeed, our special case arising from modified Plebanski is of this form, just that these couplings have special values. They satisfy these equations. And if they satisfy this equation, well, then it happens that the terms in derivatives has a special shift symmetry. So that you have an additional gauge symmetry in this case, which eats up 5 degrees of freedom. Okay. So if you do use these special couplings, in fact, you have one coupling left over, which is the difference between rho plus and rho minus. That's proportional to 1 over gamma, the Barbero-Misi parameter. In fact, that parameterizes you this parity violation I was mentioning. And this parity violating term in poor length metric gravity, you do not have a parity violating term. It does not affect the equation of motion. In this case, it does. And so it leads to a mixing of cross and plus polarizations for your TT modes. And well, that's quite interesting because it gives you one avenue to measure the Barbero-Misi parameter. And the problem is that so far, there are not many proposals or no proposals to actually measure this parameter. Okay, if you take this action, well, it's straightforward to integrate out all these chi fields. You get basically a form of propagator we have seen. And if you, as I mentioned, if you take these special values, you do get this propagator Jan complained about, but for all others, you do get more poles. For all other values, you do get more poles. Okay. Well, that I told you this part in the continuum. Again, we did it originally for Euclidean signature. What happens if you take Lorentzian signature? I mentioned that these chi plus minus, they stand for self-dual and anti-self-dual. If you go to Lorentzian signature, the self-dual, anti-self-dual equations gets an I. So you have complex fields, which kind of also appear in the Aschdecker connection a priori. You can introduce the real imaginary parts. But then what happens is that, so your positive quadratic forms turn into indefinite terms, which might be a problem as it leads to instabilities. Actually, this is well known and happens in electrodynamics where, sorry, that should be the Lagrangian. The Lagrangian in Euclidean signature is E² plus B², and in Lorentzian signature is E squared minus B squared. But in that case, we don't care about it because E and B are not independent fields. But in our case, they are. So what happens? We did basically the full canonical analysis of the linearized system. And so you get a Hamiltonian, which you see here has many terms. And if you look very closely, you see that there are some negative definite terms. So these definitely appear. And you would be a priori concerned because if you take a harmonic oscillator and then minus a harmonic oscillator and then couple these two oscillators, in general, you find complex frequencies and unstable dynamics. But in this case, despite this complicated form, it turns out that these negative, well, the negative part and the positive part, in the end, you can decouple. So the massive modes have negative energy, but they decouple from the massless modes. And so according from John, I learned in the talk, this is very much having a positive definite Lagrangian and then having a part which is negative definite. So this can be interpreted as modes propagating backwards in time, if you want. In any case, we have this issue. And we confirmed that at least these negative masses appeared in this in the lattice calculation. Okay, so to summarize, well, we found area matrix from spin forms in 3 different ways. On the microscopic level, so I didn't talk about that, but you can kind of map all the quantum numbers you get for 4 simplex to an area matrix for the 4 simplex. Like on a mesoscopic level, these would be the area-Ricci calculations. You find a continuum limit, which can be described by an area metric action. And you can also do and go completely to the continuum and work with a modified Plebanski framework, where you again derive an area metric action, and these results here are consistent. So to summarize, we see area metric appearing, in particular in spin forms, but they seem to be around in several quantum gravity approaches. We have a new parameter, the Barbero-Emisi parameter, which has these 2 forms of parametrizing parity violations, but is also an anomaly parameter. Well, we find these indefinite actions for the anti-self-dual fields. So what that means is that, well, if you manage to define an LQG Hamiltonian, that might not be positive definite. I think Lee, when I started my first postdoc, was asking me to prove it's positive definite. Also, everyone agreed it's not well defined, but in any case. So if you heard about it, it's very similar to an effect which appears in the Kodama state, where for Lorentzian signature, you get also an indefinite signature and a norm which is not well defined. But for Euclidean signature, it's completely positive. And we have a possible observational signature for the Barbero-Emisi parameter because you get kind of effects from the parity violation, even in the linearized dynamics. Just let me, the last slide, okay. But it's ongoing work to look at area metric actions to higher order, so nonlinear order, and consider the area metric renormalization flow. So much fun. Anyway, so we hope to kind of look a bit at the flow of the Barbero-Emisi parameter and well, also investigate this case with additional kind of symmetry in the kinematical term. So this peculiar propagator. By looking a bit at phenomenology, so solutions of area metric gravity or non-local Weyl gravity with spherical symmetries and black holes. And well, one can kind of take modified Plebanski and the effective spin form action and the lattice and try to define it for cosmological backgrounds, meaning FRWs. And so overall, well, we now have an action which kind of captures some essential effects of spin forms, and so that we have it in the continuum, so that it opens up new avenues to spin form phenomenology, in particular, since indeed doing these Lorentzian non-perturbative calculations is very difficult, but we are still working on these non-perturbative path integrals, of course. Thank you.
Yeah, thanks a lot, Bianca. We have time for maybe one quick question with a quick answer. So much.
Now, what you're calling a graviton, in what way is this different from the kind of, gravity wave, graviton idea that you have? Is it the same thing? I mean,
What is different from classical gravitational waves? Yeah. No, it's not. It's not. No, they are the same character. It's really that, okay, I indeed take the linearized area Ricci action, and so the kind of non-trivial part is to compute the linearization on this lattice. But given that, you can identify among these humongous amount of degrees of freedom a length metric. And one way to do it, it happens that these are always 10 massless degrees of freedom. And that, like after you integrate everything else out, it will always lead to the linearized Einstein-Hill or Fields-Pauli action. And I guess that's just due to universality in the sense that this is the only diff invariant choice of which you can get, at this linear order. And so that is the same. So the difference is that there are, in the area metric case, there are additional degrees of freedom. I mean, there are more degrees of freedom, which lead to effects at higher order in the derivatives, like the y squared, but they are suppressed in this case by these masses, which are defined on, which are order 1 in terms of the lattice length. Yeah, so it's still quadratic order in the fluctuations, but it's higher order in derivatives. But all these additional terms have a mass. And so this mass suppresses all these effects. And this is of order, if you take Planck length as a lattice length, it will be Planck mass. Okay.
Okay, I think we have to continue. Let's thank Bianca again.